The 12-fold way provides a nice roadmap of what we'll be doing in combinatorics. Now, when I give this lecture to my discrete mathematics class at Harvey Mudd College, I tell my students not to take notes this time. None of this material will be on the test, nor will you need it for the subsequent lectures. But if you come back to this lecture after you've gained some more combinatorial experience, you'll find that it will make more sense. I think all the lectures in this course are worth a second viewing, but this one is especially worth it. Now, this lecture is all about a combinatorics problem about a combinatorics problem. Consider the question: how many ways can we place X pieces of candy into B bags? Now, B stands for the word bags. X stands for extremely sweet pieces of candy. Now, the answer to this question depends on a few factors. Are the candies distinguishable, like these? They come in different shapes and sizes and flavors. Or are the candies instead like these, where they all look alike? Okay, so also we could ask about the bags. Do the bags all look alike? Is one bag just as good as any other? Or perhaps the bags have been labeled so that maybe one of those bags is for Laurel, one is for Ariel, one's for Dina, and one's for me. Okay, so there are a few possibilities. Also, are there any restrictions on the bags? For instance, maybe a bag can carry any number of candies, or maybe they can hold at most one candy, if the bags were really small, or maybe we will insist that each bag be given at least one candy so that nobody ends up empty-handed. So my first question is, how many different combinatorics questions can come out of this question? So we saw that there are two possibilities for the candies. Either they are distinguishable or identical. There are two possibilities for the bag. They're either distinguishable or identical. There are three possibilities for the capacities of the bags. They could either have any number of candies, at most one candy, or at least one candy. So by the rule of product, there are 2 times 2 times 3 possible questions, 12 possible questions. We can represent these problems in the following table, sometimes referred to as the 12-fold way of combinatorics. Of course, there are other variations that we can add, like does order matter inside of each bag? For these problems, we'll assume the answer is no. Everything that's in a bag, the order doesn't matter inside of it. All that matters is the contents of the bag. If order mattered, that would give us another dozen problems, and 12 is plenty. Okay, so once again, here is our table of the 12-fold way. How many ways can X candies be placed into B bags subject to these restrictions? Now, for certain values of X and B, the answer is obviously 0. For example, if X is bigger than B, if I have more candy than bags, then there's going to be no way for each bag to get at most one candy. So that second column is going to be 0 whenever X is bigger than B. Similarly, if B is bigger than X, if I only had, say, 2 pieces of candy and 4 bags, then there's no way that I would be able to distribute the candy into the bags in such a way that every bag gets at least one candy. Okay, so those situations are clear. We'll focus on the situations where the answer is not 0. The good news is that we can already answer many of the questions in the 12-fold way table just from what we've learned in Lecture 2. So let's do those now. These 3 answers should be ones that you can figure out right now based on what you already know. Let's do the first one. Suppose I have B distinguishable bags and X distinguishable candies. All right, then how many ways can we distribute the candy to the bags? And there are no restrictions on the bags. Some bags can be empty, some bags could have several of them, anything goes. So the first candy has how many choices? It has B choices, okay, so I put it in this bag. This candy also has B choices. This candy has B choices, and so on. So there's B times B times B, X times B to the X ways of doing that problem. On the other hand, suppose that the bags are allowed to have at most one candy. Then I have B choices for my first candy, but now my second candy, instead of having B choices, since the bags can only hold one or zero, since the bags can hold at most one, then I'll have B minus 1 choices for the next one, then B minus 2 choices for the next one, and so on. So with X candies all together, we have B times B minus 1 all the way down to B minus X plus 1. Otherwise known as B factorial over B minus X factorial ways to distribute them in this situation. Okay, now suppose the bags are still distinguishable, but the candies are identical, and the bags still are only allowed to hold at most one candy. All right, then what's the situation? Now, all these candies are identical. Let's say I had just 2 candies, and I have four identical, actually, in this case, 4 distinguishable looking bags. So these bags are all distinguishable. I just have to choose 2 of them that are going to get a candy, like this one and this one. How many ways can I do that? No bag's allowed to get 2 or more. So there'd be 4 choose 2 ways of solving that problem. Or in general, with B bags and X candies, there'd be B choose X ways of deciding which B bags get the candy. And if X is bigger than B, then we know that B choose X is 0. There are 2 other entries in the table that are easy but not very interesting. Okay, and if each bag is allowed to have at most 1 candy, and if the bags are identical, okay, so here's the identical situation where all the bags look alike, but the bags still are only allowed to have at most 1 candy. Then, how many ways could I distribute X candy into those B bags? Again, if X is bigger than B, if I have more candy than bags, the answer is 0. And if I have less candy than bags, like say I have 2 candies, let them be distinct candies, I've got these 4 identical bags, then how many ways can I distribute them? Well, you would say I could go here and here, but that's the same as going here and there, right? Because the bags are all identical. Every candy is going to get its own bag, so there's only going to be one way to do it, whether your candies are distinguishable or identical. Okay, so those are the next 2 entries of the table. All right, the next situation, now we're going to encounter some new situations. Suppose I have X identical candies and I have B distinguishable bags. Then how many ways can I do this problem? The answer is a familiar looking answer. It's a binomial coefficient. It's X plus B minus 1 choose X. That's the answer. We understand what the answer says, but how do we derive that? We derive it by what's called the method of stars and bars. We'll learn about the method of stars and bars in Lecture 5, but here's a sneak preview of what it's all about. You might call this next example the method of candies and bars, or the candy bar method, if you will. Okay, so how many ways can we distribute, let's say, 10 identical candies into 5 distinct bags? Okay, I even have a 5th bag here, all right, and so it's different from the rest because it doesn't have a label on it. So I've got 5 distinct bags, 10 identical candies. So for example, we might allocate our candies this way, as I'm showing you in the figure. to indicate that bag 1 gets 2 candies, and bag 2 gets 5 candies, and bag 3 gets a candy, bag 4 gets a candy, bag 5 gets a candy. Notice where I put my bars, my dividers, to indicate how many each bag got. Or we might allocate them this way. Now, by having the divider right at the beginning is telling us that bag 1 is empty, then bag 2 gets 3, then bag 3 gets 1, bag 4 gets nothing, and bag 5 gets 6 candies. So, do you agree that the number of ways to allocate the candy into these distinguishable bags is exactly the number of ways to arrange these 10 circles, these 10 candies, and 4 bars? Right? So, and so I have these 14 objects, 10 candies and 4 bars. And how many ways can I decide where those bars are going to go? Well, there are 4 bars out of 14 spaces they could land on. There's 14 choose 4 ways of doing it. Or focusing on the candy, there would be, with 10 circles there, there's 14 choose 10 ways to distribute the candy. When we have X candies and B bags, then the problem is to count the number of ways to arrange X candies and B minus 1 bars. We have B minus 1 dividers, and that can be done X plus B minus 1, choose X, different ways. Okay, so that explains that entry of the table. Let's go to this one. Suppose, again, my candy is identical. My bags are distinguishable, but now every bag has to get at least 1 candy. Well, in that situation, what do? You say every bag needs at least 1 candy? Okay, let's give each one of them a candy. The candies are all identical. And now we've reduced the problem to the earlier problem. Now we just have B fewer candies than we had before, right? And so now instead of distributing X candies into these B bags, we'll have X minus B candies to go into that bag, into the B bags. So replacing X with X minus B in the problem we just solved, we would get X minus B plus B minus 1, choose X minus B, which is equal to X minus 1, choose X minus B, which is also equal to X minus 1, choose B minus 1. That gives us the simplest, prettiest answer, X minus 1, choose B minus 1. Okay, next we move to the situation where we're dealing with distinct candies and identical looking bags. And now, well, we get stuck a little bit. We're going to focus on this situation, and we have the restriction that every bag gets at least 1 candy. Okay, so I'll say it again. This is the number of ways to distribute X distinct candy into B identical paper bags where each bag must get at least 1 candy. I'm going to, you might say, cop out a little bit. I'm going to define the answer to this problem as SXB, where SXB is called a Stirling number of the second kind. And here's what SXB is. So SXB is simply the answer to this question. Now, so for example, if I have 11 distinct pieces of candy and 4 identical brown paper bags, or red paper bags in this case, then there are how many ways to answer this question? S11 4, in such a way that none of the bags are empty. Notice that since the bags all look alike, this allocation of this allocation here would be the same as this allocation there, right? Because all the bags are identical, then those would not be different. On the other hand, if I, say, switched this candy with this candy, these would be different arrangements, right? Because the gold candy was with the black jelly bean in this situation, whereas in that situation, the red candy was with the black jelly bean. Okay? We'll eventually come up with a formula for SXB in Lecture 6 when we study the principle of inclusion-exclusion. But for now, we'll just content ourselves with answering this question as SXB, a Stirling number of the second kind. By the way, in case you were wondering, we mentioned these were called Stirling numbers of the second kind. If you were wondering what Stirling numbers of the first kind are, they count permutations of X objects with exactly B cycles. We'll briefly talk about permutations and cycles in Lecture 13 as we apply number theory to the mathematics of card shuffling. Once we know Stirling numbers, there are two other entries of our table that we can get pretty quickly. For example, let's go back to the situation where the candies and the bags are distinguishable. Then how many ways can I do that same problem where every bag has to get at least one candy? Well, it's the same as the last problem. First, pretend as if the bags were identical. Distribute your 11 candies or your X candies into the B bags SXB ways, and then make the bags distinguishable by putting labels on them. Decide which of those bags is for Laurel, which is for Ariel, which is for Dina, which is for me, and how many ways can we do that? Here we could do that 4 factorial ways. In general, you'd be able to do that B factorial ways. And so the answer to that problem is going to be B factorial times the answer to the previous problem. That is B factorial times SXB. All right, now what if our bags are identical, but we allow some bags to be empty? So I'm going to the case where I don't have any restrictions. Some bags are allowed to be empty. My candies are all distinguishable. Then how many ways can we do that? Well, here we say, well, if all the bags had to have something in them, we know there were S11 4 ways of distributing those 11 candies among 4 identical bags. On the other hand, if they don't all have to be have something in them, then I'm either going to have 4 bags or 3 bags or 2 bags or 1 bag. So the answer is S11 4 if they're all full, or S11 3 if 3 of them are full, or S11 2 if 2 of them are full, or S11 1 if 1 of them is full. Okay, so and the others are empty. All right, so since the bags are identical, we get our answer of S11 1 plus S11 2 plus S11 3 plus S11 4. And in general, now if we want to use summation notation, which we'll introduce in Lecture 4, the answer would be the sum of S11K as K goes from 1 to 4. And for an arbitrary X and B, the answer would be the sum of SXK as K goes from 1 to B. I'll use that compact notation since it fits in our table nicely. Finally, we turn our attention to the bottom row of the table where the candies and the bags are identical. So I'm going to put all these distinguishable candies away. Only deal with identical candies now. And all my bags are identical too. All right, so the problems in this row are sometimes called integer partition problems, in contrast to the problems in the third row, which are sometimes called set partition problems. So the question is, how many ways can I put X identical candies? How many ways can I put them into B identical non-empty bags? I'm going to do the situation where every bag has at least 1 candy. Again, we're going to begin by inventing an answer. We're going to call the answer to this problem PB of X, which stands for the number of partitions of the number X, the integer X, into exactly B parts. So for example, let's say I have 6 identical candies. Here's 6 identical candies and 3 identical bags. Now, how many ways can I distribute these 6 candies into 3 identical bags? I can either go 4 in a bag, then 1, then 1, which is the same as going 1 and 4 and 1, right? Because the bags are identical. So I can either do 4 plus 1 plus 1, or I could do 3 plus 2 plus 1, or I could do 2 plus 2 plus 2. That's it. Those are the 3 ways, because everything's identical. The bags are identical looking. The candy's identical looking. There's just 3 ways of doing it. So we say that P3 of 6 is equal to 3. Here's another example. Suppose I had 10 identical candies to be placed into 5 identical bags. Then that can be done in exactly 7 ways. Now, I'm not going to actually do the distribution here, but you can think of this is why we call this an integer partition. We're taking the number 10 and we're breaking it into smaller numbers. So 10 can be thought of as 6 plus 1 plus 1 plus 1 plus 1. Or you could write the number 10 as 5 plus 2 plus 1 plus 1 plus 1. And notice I'm writing my numbers in decreasing order because since the order doesn't matter, some bag gets 5, some bag gets 2, some bag gets 1, some bag gets 1, some bag gets 1. You may as well write them in decreasing order. And here we have 7 ways of doing it, so P5 of 10 is 7. When the objects are identical, the number of ways of putting candies into bags is smaller than when things are distinguishable. So it's a little bit surprising that there's actually no simple formula for partition numbers. Although there are ways of calculating them through a recursion, and we'll say more about recursions in lectures 7 and 8, the best answer we can give to the number of ways to put X identical candies into B non-empty bags is PB of X. For the last entry of our table, let's consider the situation where some of our bags are allowed to be empty. For example, I may have 6 identical candies and 3 paper bags. Then we know that there are P3 of 6 ways that use exactly 3 of the bags. How many use just 2 bags? Well, P2 of 6, which is also equal to 3, because you could write the number 6 as 5 plus 1, or 4 plus 2, or 3 plus 3. How many use just 1 bag? Well, P1 of 6, which is just 1. Put all 6 candies into 1 bag. Altogether, there are 7 ways to allocate the candy. 3 plus 3 plus 1, or P3 of 6 plus P2 of 6 plus P1 of 6 ways. Or if we want to write this using sigma notation, that's equal to the sum of pk of 6, as k goes from 1 to 3. And in general, with X candies and B bags, the number of allocations would be the sum of pk of X, as k goes from 1 to B. And that gives us the final entry of our 12-fold way table. Isn't it beautiful? Let's look at some numbers to see if our table looks reasonable. Okay, so with 5 candies and 10 bags, if we plug into all the formulas from our 12-fold way table, these are the numbers that we get. Now, whenever I look at numbers, I like to sort of apply a sanity test to them. That is, are these numbers reasonable? What sorts of things should always be true, no matter what numbers I'm using, whether it's 5 and 10 or something else? Well, clearly the top row, where the bags are different looking and the candies are different looking, there should be more ways of doing that stuff than when some of the objects are identical. So the top row should always dominate all the rows beneath it, and you can see clearly here that it does. Also, the first column where we have no restrictions on the bags. Some bags can be empty, some bags can have more than one object. Then there should be more ways of doing that than the situations where the bags are restricted, where a bag can have at most one candy, or a bag needs at least one candy. So the first column should dominate the second and the third column, and it does. Even the bottom row, where everything's identical, that should be the least ways of doing things, right? That should be dominated by the third row and the second row, and you can see that that happens too. On the other hand, with 10 candies and 5 bags, that's the situation I have here, then we get these numbers, right? Notice these numbers are quite a bit bigger, but the same sanity test applies. The first row dominates the rows below it. The leftmost column dominates the other two columns. The bottom row is less than the rows that are above it. And just for fun, let's see what happens when x and b are equal to the same number n. Here we get, this time instead of having zeros in a given row, because we no longer have more, we don't have b bigger than x, we don't have x bigger than b, both b and x are equal to n, so we have a bunch of ones this time. And look at the numbers that we have. They're familiar numbers to us. There's n to the n, an exponential type function. There's n factorial appearing twice. There's a binomial coefficient, 2n minus 1, choose n, appearing. And we've got these two other numbers, b of n, which stands for the nth Bell number, and that's just the sum of the Stirling numbers. And p of n is is known as the nth partition number, and that's the number of ways to partition the integer n into any number of parts. Whereas the rightmost number, we had to have partitioning n into exactly b parts. Here we're partitioning it to any number of parts. Let's say a little bit more about partition numbers. So partition numbers are usually defined this way. pk of n is the number of ways to express the integer n as the sum of k positive numbers, where order doesn't matter. So for example, P3 of 6 is 3 because 6 can be written as the sum of 3 integers in 3 ways. 4 plus 1 plus 1, 3 plus 2 plus 1, or 2 plus 2 plus 2. Since the order doesn't matter, I list the numbers again in decreasing order. Equivalently, you can say that pk of n is the number of ways to distribute n identical candies into k identical bags with no empty bags, as we saw before. Some values of pk of n are obvious. For instance, when n is greater than or equal to 0, pn of n is equal to 1. We just put 1 candy in each bag. Likewise, for n greater than 0, p1 of n is also equal to 1. If I only have 1 bag and n identical candies, guess what? They all go into that bag. And if there are more bags than candy, then pk of n is 0 whenever k is bigger than n. But what about the non-obvious situations? If there's no formula for pk of n, then how do we compute it? The answer is by using a recursion. That is, by expressing pk of n in terms of smaller problems. For example, when computing p3 of 6, we can break the problem into 2 cases. Either the smallest bag has size 1, or the smallest bag has size that's more than 1. Okay, so how many where the smallest bag has size 1? If I have 6 pieces of candy, then that would require us to have 2 bags for the remaining 5 candies. And that can be done, how many ways to put 5 identical candies into 2 bags? P2 of 5 ways, which is a smaller problem. In fact, P2 of 5 is 2 because you could distribute those candies either 4 and 1 or 3 and 2. Again, remember, my bags are identical. Okay, how many where the smallest bag has more than 1? Well, if the smallest bag has more than 1, that means all the bags have to have at least 1 it has to have more than one candy in it, right? If the smallest bag has more than one, and we still have 3 bags to fill with the remaining candies, and that can be done P3 of 3, that is, one way. Therefore, P3 of 6 is equal to P2 of 5 plus P3 of 3, which is 2 plus 1, which equals 3. And in general, for k between 1 and n, we get this recurrence, pk of n is equal to pk minus 1 of n minus 1 plus pk of n minus k. This would allow our computer to calculate pk of n for any specific value of n and k. As I said at the beginning of the lecture, don't panic if some of this material went by a little quickly. It's a good preview of things to come, and it will definitely make more sense if you come back to this lecture later as you become more comfortable with combinatorial concepts and arguments. In our next lecture, we go more deeply into the combinatorics of combinations as we explore the beautiful properties of Pascal's triangle.